Our sand systems are completely automated. The large tank that you see on the right holds approximately 100 tons of sand. The green round cylinder on the far right is a mixing unit, and they're mixed automatically, where there are probes in the inside of the unit that call for sand and discharge sand. The computer systems are set up. We're mixing about 3,500 pounds of sand per batch in about a minute and a half per batch. Sand is moved by conveyor underfloor through an elevator overhead over the conveyors into the respective molding machine. This is an automatic molding machine. This is the first horizontal molding machine of its type built about 2001. What you see here is cores being set into a mold, and we'll look at that a little closer during the next cycle. These machines operate about 120 molds per hour. While the mold is being processed or pushed out for pouring, it's setting cores in place for the next cycle. And you can see these cores are locked into position very tight. The mold is being made right now. It's being squeezed. Sand was just blown into the mold. Now it's going to what we call strip, where the drag comes down, the pattern will index to the right. You can see the bottom, we have the same thing on the top, the opposite half of the two. The cores are being held in position. When he pushes a button, which is normally automatic, it'll set into the mold. Now you see the cores in position. That will index back below the other half. The tube will close, and the process starts over again. You saw that he was putting a screen into the mold. The reason we do that is that this is a fiberglass screen. All the liquid metal that goes into the mold passes through that screen to assure there are no inclusions or no impurities in the metal that could get into the casting and cause a fracture. We're melting about 5,000 pounds of aluminum an hour. This is one of the newest technologies of its kind, what we call a stack melter. And the reason that it is relatively new, it was built in Germany, but what we're doing is we are using our stack gases to preheat our metal. Aluminum has a tremendous affinity for oxygen. It wants to absorb oxygen at a very rapid rate. So that what we try to do is get it from a solid state to a liquid state just as quickly as we possibly can. The faster we can do that, the less oxidation losses. What we mean by that is that when we put 100 pounds of material into a furnace to melt, that doesn't mean we get 100 pounds out. The oxidation rate that is very fast, we are losing 3 or 4%. With the metal costs being as high as what they are, that is a very costly consideration. So what we want to do is we want to get that from a solid to a liquid just as quickly as we can. So what we're doing in this case is we're using our stack gases to preheat. And the reason you see a load of material in there to go into the furnace, and there's a computer that we'll see when we get up on the platform that is set at a given temperature, so that as the stack clears and the temperature rises, that's saying that the stack is open and another charge will automatically go into the furnace. This is a computerized system that controls the furnace. The amount of energy going into each burner, the amount of fuel, we are melting with gas and holding with electric. And this tells us where the exact allocation of material and fuel going into each of the particular units. The temperature settings on the furnace, we're melting the metal and holding it at about 1400 degrees Fahrenheit. The metal is melted, transferred into a bath area inside the front of the furnace. At a point in time as the furnace is low, we will duplex metal into our holding furnace. As the metal transfers into the holding furnace, you see there's a rotary, that is what we call a rotary degassing unit. As I said earlier, aluminum has a tremendous affinity for absorbing moisture, or for absorbing oxygen. So that what we do is we're introducing nitrogen through that rotary degasser, which evolves and combines with the nitrogen, or the hydrogen that is in the metal, and causes it to raise. Right now Bobby's tapping and filling the furnace. The additions that it's putting into the metal, is what we saw on the graph and on the TV screen. That is to generate that modified condition. And his filling the furnace on a regular basis. What happens here, as the metal moves through the furnace after the degassing, there's a permanent ceramic filter that sits under this metal pump. And we call it a metal pump because that's a generic name for the industry. But what it really is there are no moving parts. There are two coils that are embedded in ceramic in a liquid bath of metal. And as the energy is applied to those two coils, the energy causes the metal to raise and feed through that launder and feed into the mold that you see pouring. And what we do is each job has a unique program, and as we alter that program, we can speed the flow of metal or slow the flow of metal depending on what we want for a particular job. I might add that all our programming is done by our people in the plant. As you see when we get into our classroom, we put a lot of energy and effort into the training of our people, and our people have been very receptive to that idea, so that what you saw in the lab, those are individuals that actually process our metal. They are not lab technicians per se. You see the material handling is completely automated. The part is cooling now. It's still, it is not quite solidified. It's still on the soft side. You can see that it's still give and move. But to go through the entire cooling system, it will be completely solidified. Castings solidify, they're removed automatically from the mold. The sand readily breaks away from the metal. You see a mold coming up the system right now. All right, the sand, this is what we call a shakeout. The sand goes through the shakeout, returned on a conveyor under the floor, back to the sand, back to the sand system for reprocessing. The castings continue on the conveyor on up to our secondary processing area. The sand is reused over and over and over again. We're what we call a green sand foundry. And we need to explain that. What we mean by green sand is the fact that the sand is not baked. You see that the sand is actually a dark brown, almost a black, and that's done because of the carbonaceous materials in the sand. As the high temperature hits those carbonaceous materials, they will burn and create a certain amount of carbon, and you see the black sand. If we would take a sample of that sand, which we do from time to time, take it into our lab, and we would bake that sand at 1600 degrees Fahrenheit, that sand will return to literally the original color that you would see on the beach. And that's what it is. It's silica sand. It's very common to the sand that you have on the beach.